All right, welcome everyone to The Explainer. Look, if you're building or training massive deep neural networks, you already know that distributed systems are just an absolute necessity. I mean, scaling your training from weeks on a single server down to hours on a cluster is incredible. But it brings up this really fundamental systemic tension. We're constantly fighting this battle between iteration quality, meaning, how mathematically consistent and accurate our gradient updates actually are, and iteration quantity, which is simply how many of those updates we can shove through our GPUs per second. So today, we're unpacking a total masterclass of a thesis by Xing Zhao that tackles this exact bottleneck. We'll be introducing two profound models, DynamicSSP and ElasticBSP. We're going to explore how they fundamentally rethink synchronization by literally co-designing the system architecture alongside the intrinsic optimization properties of machine learning itself. Okay, let's dive into this. Here is our roadmap. We'll start with the synchronization dilemma, move into DynamicSSP, unpack the fully connected layer problem, and then break down ElasticBSP before looking at the empirical results and future directions. Let's get right to it. Section 1. The Synchronization Dilemma. To ground us visually, let's talk about data parallelism. Scaling this across heterogeneous clusters, where you might have a weird mix of P100s and 1080s, or you're dealing with varying network latency, well, it creates massive inefficiencies. The hard truth is, your entire cluster is literally only as fast as its communication architecture. As machine learning researchers, you know the drill here, right? The full deep learning model is replicated across all your worker nodes, and the training dataset is sharded. In every iteration, each worker computes its gradients via stochastic gradient descent based on its local batch, pushes those gradients up to the server, and pulls down the updated global weights. It sounds super elegant in theory, but in practice, workers just do not process data at the exact same speed. Some blaze through it, while others just drag behind as stragglers. And that leads us straight into what we call the optimizer's dilemma. Traditionally, we've had two extremes. Over on the left, you've got bulk synchronous parallel, or BSP. This imposes really strict synchronization barriers at the end of every single iteration. The parameter server literally has to wait for every single worker to push their gradients before it updates the weights. Sure, this guarantees amazing iteration quality, but it completely destroys iteration quantity. Why? Because your absolute fastest GPUs are just sitting there idle, burning precious wall clock time waiting for the slowest straggler to catch up. Then, on the right, we've got asynchronous parallel, or ASP, zero waiting. Workers push and pull whenever they feel like it. You get massive iteration quantity, but terrible iteration quality, because those slow workers eventually push heavily staled gradients, which injects this massive noise that can completely derail your convergence. So, to bridge that gap, the field adopted Stale Synchronous Parallel, or SSP. SSP basically allows workers to run asynchronously, but only up to a very specific point. It establishes a bounded delay. It limits the difference in iterations between the fastest and slowest workers to a fixed threshold, which is just a hyperparameter. If a fast worker gets too far ahead, boom, it's paused. Now, this is a great middle ground, but there's a pretty fatal flaw here. That fixed threshold is incredibly brittle. A static hyperparameter simply cannot adapt to the dynamic, fluctuating realities of real-world cluster environments. Which brings us to Section 2, introducing DynamicSSP. This right here is the first major conceptual breakthrough of the thesis, making a leap from rigid parameters to truly adaptive communication. Instead of locking the whole cluster into a single guessed hyperparameter, DynamicSSP shifts the decision-making online. The parameter server actively tracks the iteration progress of the slowest worker in real time. It then actually calculates a dynamic staleness threshold on the fly within a defined range based entirely on the current processing speeds of the cluster. So when a fast worker sends a push request, the server evaluates it against this newly computed dynamic threshold. It only halts that fast worker if it breaches that specific real-time limit. This is huge because it allows the system to seamlessly absorb transient network hiccups or temporary GPU slowdowns without unnecessarily pausing your fastest nodes. Moving to Section 3, the fully connected layer problem. Now, what's really interesting here is a massive empirical anomaly the researchers uncovered. When they tested DynamicSSP on pure convolutional neural networks like ResNet, SSP and DynamicSSP actually perform wonderfully. Since CNNs share parameters across the image via filters, they're surprisingly robust against asynchronous noise. But, and this is a big but, when we try applying these asynchronous paradigms to massive models that contain fully connected layers, or FCLs, things like VGG16 or AlexNet, they fail spectacularly. I mean, FCLs have millions of independent, non-shared parameters. They are just incredibly sensitive to staled gradients. In the empirical tests, if you let staled gradients infect an FCL model, the loss curve stalls out, and the model literally diverges. For these massive structures, bulk synchronization isn't just a nice-to-have, it is strictly mandatory if you want to learn anything at all. So how do we fix that? Section 4, ElasticBSP and Zipline. Basically, we're back to square one for massive FCL models. We desperately need to avoid the agonizing idle times of vanilla BSP. And this is exactly where ElasticBSP completely re-engineers the process. Instead of forcing a barrier at a rigid interval, like every single iteration, ElasticBSP lets workers compute asynchronously for a brief, highly calculated period called a superstep. The server is constantly monitoring the exact computing and communication time intervals for every single worker. Using an online look-ahead mechanism, it predicts the precise future moment where the maximum number of workers will naturally finish an iteration at roughly the exact same time. And then, it dynamically drops a synchronization barrier right at that optimal timestamp. It literally shifts the finish line to catch everyone perfectly in stride. This minimizes idle waiting time while still guaranteeing you get a clean slate of synchronized, unstaled waits. Now, as researchers, I know your immediate concern right now is overhead. Constantly predicting future timestamps for dozens of nodes sounds like an O of n squared nightmare that would just choke your parameter server. But the math here is absolutely beautiful. While an exhaustive search scales really poorly, the custom Zipline algorithm brings it down linearly. And the optimized version, Zipline Opt, it drops the computational complexity to a mere O of C, where C is just the number of future iterations you want to look ahead, and N is the number of workers. Space complexity stays at a flat O of C. It's a blisteringly fast, one-pass greedy algorithm that adds virtually zero delay to the server's operations. All right, Section 5, Empirical Performance and Results. Because, hey, theoretical algorithms are elegant and all, but wall clock time is really all that matters at the end of the day. And the hard empirical data here shows a massive 1.77x convergence speedup for ElasticBSP over traditional vanilla BSP when training these massive models. So the crucial point is perfectly captured in this training graph. We're looking at a VGG16 model training from scratch on the massive ImageNet 1K dataset, distributed across a parameter server with 4 workers. Look at the bottom dotted lines hugging the x-axis. That's ASP and SSP. They are completely failing to learn because of that fully connected layer problem we talked about. The staled gradients are just destroying the weights. The solid black line right in the middle is vanilla BSP. It's learning safely, sure, but it is taking forever because it's constantly stalled waiting for stragglers. Now, look at the top dashed lines. That is ElasticBSP. It completely separates from the pack, rocketing up the accuracy chart in a mere fraction of the wall clock time. To summarize this remarkable delta, ElasticBSP not only converged 1.77 times faster than vanilla BSP, but it actually achieved a 12.6% higher overall test accuracy. Now, you might be wondering why. Well, because a tiny, perfectly controlled amount of asynchronous variance actually acts as a regularizer. It helps the model generalize way better than the overly rigid updates of standard BSP. It totally avoids those strict barrier waiting times, heavily optimizes your hardware utilization, and successfully protects those highly sensitive FCL models from diverging. It really proves that when we co-design our distributed architecture to respect the fault tolerance properties of the machine learning model itself, we can absolutely break the optimizer's dilemma. Finally, Section 6, Future of Distributed Learning. Let's look at how this builds into the future. Dynamic boundaries and look-ahead algorithms have definitively proven that elasticity is the key to scalability here. But this leaves us with an incredibly compelling open problem to solve. If ElasticBSP requires a defined look-ahead parameter, could we eventually deploy reinforcement learning to fully automate our synchronization policies? Just imagine a parameter server that independently observes cluster latency, worker compute speeds, and the specific topology of your neural network, and then uses an RL agent to dictate bespoke, millisecond perfect synchronization barriers entirely on the fly with zero human tuning. That is the next great frontier for distributed learning. Thank you so much for joining me on this explainer. I really hope it sparks some brilliant ideas for your own research clusters.